So, hello everybody, and welcome. Welcome to the second webinar organized by the 5G CARMEN project. This is the first time that you join us, it's a pleasure to have you here. If you have already followed the first webinar, good, I'm happy to have you back. So if you haven't seen the first webinar, you can easily catch up. It's recorded and available on our social platform and on our YouTube playlist. As I said, this is a webinar organized by the 5G CARMEN project. 5G CARMEN is a project that is funded by the European Commission. It's one of the 3 corridors project, and it deals with delivering tests and pilots across the Bologna to Munich corridor, a corridor that covers 600 kilometers, and where we want to show how 5G can enable high level of automated driving also in real world conditions. The corridor spans across 3 different countries, so we have to face the challenge of providing service continuity also when we are in roaming and when we cross the country borders. In the first webinar, we have seen which are the functional elements and how the architecture that we have deployed is built. Today, we will go more in detail on the technological enablers that 5G offers to make CCAM use cases a reality. So we will see how we have built our system, which technology we have used to build up the use cases that we are trialing along the highway in the Bologna-Munich corridor. Before I forget, if you want to pose questions and interact with us, you can do it easily using the comment section in the social platform you're using. So just drop a comment, we will be able to see it, and we will leave some time at the end to answer some of these comments. So without any further ado, let me introduce our speaker for today. I'm really happy to have today here with us Professor Claudio Casetti. Claudio is a professor in the telecommunication at the Department of Control and Computer Engineering of Politecnico di Torino. His main interests are in the fields of 5G and beyond 5G networks, connected vehicles, obviously, but in general, smart mobility and IoT. So since I know that today we have a lot of topics, I quit my very, very brief introduction and leave the floor to Professor Casetti. Thanks a lot.
Okay, thank you, Roberto, for the introduction, and good afternoon to everyone, and welcome to this webinar. The title of my presentation that was introduced by Roberto is the 5G enabling technologies for cooperative, connected, and automated mobility. We would like to, in this webinar, briefly acquaint you with the technologies, the services, and the use cases that are addressed by 5G CARMEN, that have been addressed by 5G CARMEN throughout the course of the project which is now running toward its end. Listed here in this slide, you see some of the core technologies, not all of them, but some of the core technologies that the project has been focusing on. And I will then convey to you how these technologies are used for the provisioning of some of the key services envisioned by 5G CARMEN, along with some use cases which I believe you've already seen in previous webinars, Okay, let's start with technology. Let's kick off with what I would say is probably the basic technology of 5G CARMEN, around which the whole project is built, and that is the implementation of a distributed edge cloud that provides services to connected vehicles. This distributed edge cloud has been implemented across the networks of TIM for Italy, Magenta for Austria, and Deutsche Telekom for Germany. And it is based on edge cloud MEC platforms that are embedded in these three networks and enable low latency communication and low latency computing that is crucial for the use cases envisioned and chosen by 5G CARMEN. So here in this picture, you see an overview of what constitutes the 5G CARMEN distributed edge cloud. You see here there's a middle layer plus some cloud-based services, orchestration functions, those are NFV SO boxes on the top layer. These instances in particular are running on the premises of one of the partners, Wings, whereas the other part, the lower part of the edge cloud, as I mentioned before, are instead running on each of these three operators' premises. The next slide provides, and I believe it's a little bit intimidating, isn't it? But it provides a very, very comprehensive and detailed overview of the architecture of our edge cloud. It shows the details of the three edge clouds and how they are intertwined and interconnected with each other. It's an architecture that can onboard all components in each country, although 5G CARMEN is aiming at demonstrating some use cases, some services only in a specific country. So not all use cases will be demonstrated in all countries. That's the point. The system works through the interaction of vehicles with the 5G edge cloud, and with the interaction of the onboarded services, like, for example, the Manoeuvering Service that I will address later on. The vehicles are all connected to this edge cloud, which provides seamless connectivity in terms of either message brokering or maneuver recommendation, for example. And we need this orchestrator layer because we need to guarantee that a vehicle gets the same service with coherent service instantiation as it travels from one country to another. And we expect that these services are carried out seamlessly when crossing the border. And to do that, we rely on features that are both on the network, the edge cloud, the MEC, and vehicle. The next technology that I would like to address is the Geoservice. What is the Geoservice? Geoservice is an application which is deployed on top of the edge cloud, on top of the MEC. It's a MEC application, which offers basic messaging to connected cars. Geoservice maintains an overview about all the vehicles in a given area. This overview is possible thanks to the exchange, or I should say probably the broadcasting of CAMs. CAMs are cooperative awareness messages that are defined, standardized by ETSI, and its major task, the major task of this Geoservice is to receive these CAM messages, forward them to, for example, traffic controllers, and store them and processing them. And all these messages are then, in some cases, processed to find out specific events that are occurring on the road, for example, road delays, road closures, and the Geoservice can then push back some warning messages to vehicles on the highway. This is done through what I call here the main features of the Geoservice. The main features are the CAM dissemination. CAM, as I said before, are these cooperative awareness messages. By CAM dissemination, what I mean is that the Geoservice is capable of disseminating, distributing CAM messages only to vehicles that are in a certain predefined area called the area of relevance. This area has a radius that it can be configured. So it could be either 200 meters or 500 meters or 1 kilometer around a specific point, but all the vehicles inside this area of relevance may receive these CAM messages. CAM messages, however, are just awareness messages, so they do not convey any warnings. This is instead the task of DNM's messages. DNM messages are decentralized environmental notification messages. They too are defined by ETSI, and they are also disseminated in another area which is different from the previous one that I described. It's called the destination area. The two areas can, of course, overlap, and it is defined through a geographical shape. It could be a rectangle, a circle, or an ellipse, for example. Then there is, and I'll move here to this slide here. Here it shows how the Geoservice can act as an endpoint of communication with the cars. It offers two types of interfaces. On the right, you see a message ingestion interface that is basically a generic REST interface that can be used to external applications for the purpose of injecting ETSI messages that have to be disseminated to cars. On the left, we have instead a message exposure interface, which is based on a Kafka bus. Back here, another feature that we have is the own service area support, which basically indicates the geographical area that is being served by a Geoservice. This actually means that the area of relevance, the destination areas, are all inside a much larger area called the own service area, which instead defines the coverage of the Geoservice. It's important to be aware of this own service area, especially in this project, because we in 5G CARMEN have 3 different instances of Geoservice, one for each country, and these own service area may come in touch and actually may even partially overlap across the border. This, however, is fundamental because it allows inter-Geoservice communication, which means that all the messages received from vehicle in one own service area are forwarded to neighboring Geoservice instances of other areas, as is shown here in this slide. In the slide here, for example, you see the red square and the blue square that are kind of overlapping across the German-Austrian border, and there, if there are vehicles that need to be warned or need to be notified specific critical conditions, this can be done by intercommunication between Geoservices. And basically, each Geoservices in its own service area takes care of disseminating the messages in its own portion of the distribution area, of the dissemination area, sorry. Next, we have the AMQP broker. AMQP is a message brokering protocol. Its primary scope is to enable the message exchange between information producers, for example, road operators, and service providers. And it can be used, and it is used actually in 5G CARMEN, also to send messages directly to vehicles through a specific interface called the basic interface. I will say something about this coming up in a couple of slides. This AMQP broker is, in the case of 5G CARMEN, is implemented in a virtual machine which is installed in the Mac, as one of Mac applications, the Mac used by the project. And the AMQP broker can be reached via any of the available networks, either mobile, 5G, 4G network, but also through the fixed network, because it's based on a simple TCP/IP protocol stack. To better illustrate how the AMQP broker works, you see here we have on the left side the producer, so for example, road operators who need to publish an CATS message, a warning that something is afoot, and we need to let the drivers know that there's a situation that must be aware of. So what the producer does, it adds specific geographic information in the envelope on the header of the AMQP message, and it then forwards it to the broker. The broker has, and you see it in the middle of this slide, the broker has several queues. Each of these queues are organized either by a topic, type of message, or even by a combination of type of message and areas of interest. The consumers, service providers or vehicles, subscribe to messages from to specific queues of the AMQP broker, specifying some criteria, and as a result, the AMQP broker dispatches messages to service providers or vehicles that are subscribed to events such as accidents, traffic jams, and relevant to their geographic location. This is done using a push paradigm based on geocasting. And geocasting is done through the help of the so-called Quadkeys. What are Quadkeys? A Quadkey is a string that uniquely identifies a tile, a square tile, on the terrestrial projection, calculated using latitude and longitude, and a configurable level of detail. You have to think of it as a hierarchical spatial data structure that subdivides, as you see in the slide, space into buckets of grid shape, and by adding a number to an ever-increasing string, we can focus on more and more precisely onto a certain area until actually we reach the level that we desire. And one good thing about the Quadkeys, although their implementation is a bit tricky, is that they allow users to use an arbitrary precision. So you can define how precise you want to be, how much you want to narrow down your view on a specific area, and this is expressed as a string of numbers. And if the string is too long for you, you can just remove some of the least significant digits, and you of course lose precision, but you lose precision in a linear sort of way. So it's very configurable. In terms of interworking of AMQP brokers, as you know, 5G CARMEN focuses a lot on interoperability and interworking across borders. So it is crucial that AMQP brokers get to talk to each other so that they can serve vehicles that find themselves on the verge of crossing into another country. So they are very close to the border. This is done in 5G CARMEN by federating cross-border AMQP brokers that are either in, for example, as in this picture, either in Italy or in Austria. In this way, and through the basic interface which separates the two AMQP brokers, each broker acts as a server when publishing messages to the other one, which then acts as a client. In this way, the cars that are connected to one broker can receive messages from the other one as well. In a cross-border scenario, for example, here, imagine in this picture, a car crossing toward Austria can manage to stay connected to the Italian AMQP broker, but can immediately start receiving Austrian messages as soon as it crosses the border. The next piece of technology that I want to introduce to you is one of the interesting innovations that we have brought to this project. It's called the Server Local Dynamic Map, or SLDM. Those of you who are familiar with the ETSI standard have probably already heard about the local dynamic map, which is one of the features of the facilities layer of the ETSI stack. The idea of the local dynamic map is to provide an overview of the environment around a specific car. And a car can connect information around cars that are in front, in the back, on the side, or other objects, as a matter of fact, that manage to transmit the CAM, the Cooperative awareness messages that I mentioned before. So why do we need something different? What we have here is called the server local dynamic map. Whereas the local dynamic map is thought to be implemented on a vehicle, the server local dynamic map is more of a centralized entity. The reason why we developed it is that we realized that the MEC has, for the services that it has to provide, sometimes needs some form of overview of what is going on the highway. And you can get this overview by individually asking what's going on to each vehicle. But since we already have this concept of local dynamic map, we thought, let's bring this into the backend, into the edge, and let's implement this as one of the MEC applications. In this way, the MEC or all the services that run on the MEC can at any time ask for a map of a portion of the road. This map can always be up to date because it's updated by CAMs that are received from vehicles and conveyed to the SLDM. And this is capable of guaranteeing high reliability and low latency. For example, as you see in this picture, one car may have the turn indicator on, and the other car are deciding what to do, especially if some of them are, for example, autonomous driven car, what to do with this car that is changing lane and repositioning itself on the rightmost lane. Normally, a driver would see this car, would slow down if the car is ahead, or the other car, the car in front, speeds up to open up a gap between these cars. This can be suggested as a maneuver by, as we said before, as we will see later on, a specific maneuvering service. But it requires some form of coordination. So this is where the SLDM comes into place. The SLDM provides a filtered and processed version of this data and provides it for the specific area where this needs to be put into place. So where we need the information to be conveyed to the vehicles that are about to be involved in this lane change maneuver. The CAMs are broadcasted by cars. They tell where a car is, which direction is going, what speed it is traveling at. These CAMs are collected through the UU interface by the 5G network. They are sent to the AMQP broker, which I mentioned before, and the AMQP broker dispatches these CAMs to the SLDM, which is subscribed to one of the queues of the AMQP broker. And the SLDM already also has a real-time visualization, provides a real-time visualization of the situation on the road for basically visualization purposes. So just to allow the monitoring of what is going on, allow the monitoring of what the SLDM can see, and then upon requests from other services running on the Mac, it can provide a snapshot of a specific area with indication of where the vehicles are and what they are doing. The SLDM is again implemented as in a Dockerized container running on the Mac. It is very efficient. It can provide on average, it takes on average 40 microseconds to process each received CAM. And the service it provides is well within the service level latency and 5G KPIs. That is below 10 milliseconds as required and as aimed at by the 5G CARMEN. The next piece of technology is the so-called response router. The response router is, we shall see it later in a much broader picture where response router and SLDM fit together with the maneuvering service. But the response router acts as a sort of dispatcher. So the idea is that in our use cases, several components need to cooperate and provide feedback to a vehicle. Sometimes these messages are published through the AMQP broker with topics defining a specific car to be addressed. But in general, all the other components, such as the maneuvering service that I will describe later, are supposed to be completely agnostic to the message delivery approach. So we need a piece of equipment, which is the response router, that can support other Mac components in dispatching the messages towards specific destination cars via the AMQP broker. Of course, one could embed this functionality into each of the modules that are supposed to interact with the AMQP broker. However, we chose to keep it as a distinct component because it simplifies the maintenance of the Mac applications in case there is any change, for example, in the topic name or in the topic creation rules. This also allows using the module to support services other than the ones designed for 5G CARMEN. So this is really useful going forward to create and onboard other types of services. So from an operating point of view, the response router receives a collection of messages, and each message is stamped with an identification of a destination car, as you see in the slide on the right, and then publishes the message to the AMQP broker on that topic. In this way, it facilitates the operations of the AMQP broker. To speed up the operation, all the messages are opaque to the response router. That is, the response router does not need to check its content, but it assumes just that this message through an identifier needs to be sent to the destination. The last piece of equipment, or piece of technology, actually, this is more a collection of technologies that are on board the 5G CARMEN vehicles are the V2X components. So this is a very articulated and rather complex part that has many features that help process, send and receive all the messages through either the 5G UU interface or the PC5 vehicle-to-vehicle interface. The main features are shown in this slide, and you can see them kind of bottom up. On the bottom, there are, of course, the physical layer, such as the PC5 interface, and the connection to an external 5G radio access through the 5G UU interface. And then there's all the parallel handling of peer-to-peer PC5 cooperation and client-server communication with the network through the AMQP client, which is the part that has the interaction with the AMQP broker that I mentioned before, or the Geoservice client, again, interacting with the Geoservices that I described before, or clients of specific services, such as, for example, the BSA service that I will talk about instead later on in the slides. Then on top of it, we have the facility layer, and the task of the facility layer is to provide the host vehicle with cooperative timing and positioning information that are crucial for the application layer. For example, vehicle data such as speed, acceleration are retrieved from the CAM network. You see the small box on the left, the CAM network, the controller area network of the car. So they come directly from the car sensors and therefore are highly reliable and highly up to date. Or further information can come either from the PC5 or from the UU interface. And these are all collected and presented through the facility layer to the application layer. And then there is also, and this is on the right, the box on the right, the positioning, which is received by the precise positioning unit, which is another piece of technology that I will not describe for lack of time to keep this presentation kind of compact. Okay, now at this point, we are ready to move on to the services and the use cases. And I would like to present two of the main services that are developed in 5G CARMEN using the technology that I just presented, that I just went through. One of these services is the Manoeuvering Service. Here on the right, you see graphical block scheme showing the interaction of the Manoeuvering Service with some of the service that some of the technologies that I've introduced earlier. So what is the Manoeuvering Service? Its task is to monitor the current state of road traffic and to monitor the intention of vehicles and ultimately to facilitate the maneuver of vehicles by providing them up-to-date and timely indication on what to do and how to maneuver. For example, it can determine when it is the most suitable moment to execute a lane change, or it can tell other cars to facilitate the lane change maneuver which is attempted by a third car. It manages the gaps between vehicles so that, as we have seen in the picture earlier, two vehicles may be told to widen the gap between them so that an overtaken vehicle can more easily fit in as it moves back to the right lane. In this way, the maneuver can be done safely and efficiently, even if one or more of these cars are either L3 or L4 autonomous driven cars. These recommendations, these are instead, in case of human-driven cars, are recommendations that the driver is invited to follow, again, for its own safety and for the sake of efficiency. The maneuvering service, the way we envision it in 5G CARMEN, is to implement it in both a centralized and a decentralized manner. The decentralized maneuvering service would be hosted inside each vehicle and leverages information that is just exchanged by means of vehicle-to-vehicle direct communication through the PC5 interface. And although this may entail an additional latency via the 5G UU, so the V2N, vehicle-to-network interface. However, the limited range of a decentralized implementation could result in a suboptimal handling of some cases. For example, because I do not receive all the CAM messages from all the cars around me. So for this reason, it is imperative that there is also, that we envision also a centralized version of the maneuvering service. Of course, this will be hosted. This is hosted actually because we have developed it and it's already an onboarded service, is hosted on the edge cloud on the Mac. And we have developed interfaces between neighboring Macs, between neighboring maneuvering services on the Macs for the sake of supporting these maneuvers also in proximity of border areas. The implementation has tried to be as close as possible to the state of the art, and its implementation follows a model-based control approach, which comes from the scientific literature. It consists of two controllers. One is called the tactical controller. The tactical controller computes the most efficient merging sequence and time instant, and then the operational controller generates the optimal control output, so decides when it is best to send messages to implement the maneuver that the tactical controller has identified. Another crucial service for the provision of the use cases envisioned by 5G CARMEN is the back situation awareness service. Here the idea is to target emergency vehicles and the presence of L3, L4 vehicles on the road. So emergency vehicles, when on rescue operations, must have, of course, the right of way on the road. That means that there should be a corridor, a sort of lane clearance that has to be guaranteed for these vehicles. And well, it depends on the country, because if you are in Italy, this lane clearance is normally translated in leaving some space on the right, whereas in other countries, such as Austria and Germany, this is done by opening up a corridor in the middle of the highway, and all the other vehicles move to the left of the right, the left or to the right. This could, however, be a problem because ordinary vehicles may be prevented from moving in time away from the path of the EMV. And this whole situation, this unpredictability, I would say, could become a problem for the L3 and L4 vehicles. So it could determine a borderline conditional situation for layer 3 autonomous driven vehicles. This means that in this case, the L3 system would likely disengage and hand back the control to the human. So in practice, what we try to do here is to support L3 and L4 vehicles maneuvering to clear the way for emergency vehicles on the highway. And this is done by, you see in this picture, so imagine an emergency vehicle that is dashing down the highway and starts, of course, it's got the siren on, but some vehicles may be too far away, maybe far away from either visual contact or even oral contact. So they do not see on time the arrival of the emergency vehicle. 5G CARMEN foresees a connection between the emergency vehicle and the orchestrated edge platform where the BSA service runs. And the process works so that when the emergency vehicle sends CAM messages advertising its presence and its location, it's the red arrow shown in this picture with the number 1. Then the BSA service identifies different destination areas where to disseminate warning messages or DEMS messages. For each dissemination area, it computes an ETA, an estimated time of arrival. That is, for example, it warns vehicles in an area, heads up, you've got an emergency vehicle coming up in 3 minutes. And then to other vehicles who, for example, may be already across the border, there's another warning. This instead is conveyed through the orchestrated back situation awareness service on the Austrian MEC with a different estimated time of arrival. So in this way, by proactively sending these CAM messages to neighboring MECs, this service, the functionality of this service are guaranteed also in cross-border areas. I would like to close this brief presentation by giving you an overview of the use case, 2 of the main use cases by 5G CARMEN, the cooperative and automated lane change maneuver use case, and the cooperative and automated in-lane maneuvers. What are the lane change maneuvers? They are the type of maneuvers that we have seen before. Open up a gap between 2 vehicles while a third one is changing lane and moving to the rightmost lane, sorry. And the cooperative and automated in-lane maneuvers, for example, if a vehicle is approaching another vehicle that is about to take a right exit, and this vehicle is, for example, an L4 operated vehicle, the presence of an unexpected queue on the exit could lead to the L4 vehicle to change and maybe even disengage because it finds itself in an unexpected situation. So in order to prevent this, in-lane maneuver entails having this back situation awareness alert the oncoming vehicle that there is a queue on the exit lane, so it should just change its plan. Instead of taking the exit, just continue on the same lane. So this the decision in this case is to keep going straight. As you see, this matrix shows where these use cases are implemented. As I said before, not all use cases are implemented in all the countries. And on the far right, you see the different technologies among the ones that I have described to you in this webinar that are used for each of these use cases in each of the Edge Cloud implementation. And this brings me to the end of this presentation. So I would like to thank you for your attention so far, and I'd be glad to take any questions.
Thanks a lot, Claudio. Very interesting and always very clear, your presentation. So just to...
I'm afraid I cannot hear you.
Can you hear me now?
I don't know if it's my problem.
Can you hear me? I should be unmuted. Okay. They tell me from the direction that they can hear me, so maybe it's Claudio issue.
I'm trying to use again. Sorry.
Okay, let's see if you can solve it. Now we cannot hear you. I see you speaking, but I can't hear you.
Or I can hear. Okay, I can hear you. I think it was one of the earphones that disengaged.
Okay, no problem. So, okay, just to start with we still have some time from some questions or comments from the audience. So remember that you can interact with us using Facebook, YouTube, or LinkedIn and commenting directly on the platform, and we can see your questions. I guess that people around Claudio will be curious to know at which point we are in the development of all this technology. When do we plan to deliver the final result of this test?
Okay, so we are very far ahead with the development. I would say that all of the technologies that I have presented are already in a pre-release state. They need to be tested on the road, and we are doing in this very moment. Basically, as I speak, there are tests running on the Brennero motorway in Italy and on the Austrian side, and the three operators are also engaged in providing the services and the connectivity to the cars. So we have one big demo which is planned in 2 weeks from now, and we are testing all these services for the demo. So all the technology that I have described so far are all operational right now. Of course, we are tweaking the last details so that the demos can run smoothly.
Okay, thanks a lot. Perfect. And yes, so just for your knowledge, this is not our last webinar. We plan to have more in the next week, by the end of this year, basically, and beginning of 2022. We aim to have webinars that will focus on other aspects that are being studied and developed inside the project. There will be one dedicated to the edge orchestration platform that Claudio mentioned before, that will focus on how we deliver this fundamental tool to allow a proper flexible service management and help in the providing service continuity when we move from one operator to the next, to the another one. We will have also a webinar dedicated to business modeling. It's something that we have inside that we are studying also inside 5G CARMEN. And then for sure, as Claudio said, we are testing. We have done already a lot of tests, and we are working with our technologies now. And so we will have a webinar dedicated to share the result of these tests as soon as they are consolidated. So I don't see any other questions or comments. So if there is anyone, you can still comment even offline once the webinar is finished. We will be able to see them. It will be a pleasure to answer, interact with you. Thanks a lot for joining us. Follow us. We have a dedicated website. We have social platforms both on Twitter and LinkedIn, so you can easily connect with us and stay in touch. Subscribe to our newsletter if you want, so that you don't lose any one of our development. With that said, I think that for today it's all. Thanks a lot for your participation. Thanks a lot, Professor Casetti, for your very clear presentation. It was a pleasure, and hope to see you soon in the next webinar.
Goodbye from me as well.
Bye.